Swayam Prabha. Digital India. Educated India.
Welcome friends, this is lecture 3 of this course, Flight Dynamics and Performance, MATLAB and Simulink. In the last few weeks or in the last few classes, I have been drawing a figure where we have a resultant vector which is acting over at some point. Alright, what was this point? That we will focus in today's class. Alright, so let me just draw a figure again. So this is a cambered airfoil. As you can see, the camber is existing. We have, this is the angle of attack, this is velocity v infinity, and we considered some point over here where we have a resultant vector r. Alright, and then we resolve this component parallel and perpendicular to the velocity vector. The one which was perpendicular, that is the lift, and the one which is parallel is acting opposite to the velocity, that is nothing but the drag. Alright. So now where is this point actually acting? So that is the point of discussion for today. Alright. Where is this point actually acting? Now what is this point? Some of you might already be aware of what is this point. So this is nothing but the resultant of the vector that we obtained, that we got because of the pressure and shear stress distributions. Alright, so which are impressed over the whole surface. Alright, so these are like a distributed loads. These are like a distributed load. Remember, we discussed in the last class as well, these are all the distributed loads where we have, this is the pressure which is acting at different points. So these are distributed loads. So these distributed loads are actually impressed over the whole surface. Impressed over the whole surface. Alright, and the net effect of these distributed loads is production of the resultant vector. Let me just denote it by capital R over here. And this vector is applied at a point. This vector is actually applied at a point on the body. Now, how to find such a point? This also we have discussed. You can find this point by using the centroid. Alright, centroid of this distributed load. You just have to find the centroid of this distributed load. That is from integral calculus. Then you will get a point. That point is nothing but center of pressure. Alright, CP. So the definition you can mention over here is the centroid is the point through which equivalent force acts. Right? And this point is called center of pressure. Now let me draw the figure once again so that it is more clear. So this was the airfoil that we had. Here we had pressure which is acting normal to the surface. Alright. And another source of aerodynamic force was shear stress. Alright. This is P, this is tau, this is shear stress. Always acts tangential to the surface. Alright. Now equivalent of this figure would be having the forces at a point center of pressure. So this point is center of pressure. So here in center of pressure we have the lift vector as well as the drag force. Lift force and the drag force. So these two both are equivalent to each other. Alright. And one more thing you must have noticed here, that there is a center of pressure, there will obviously be no movement. Okay. Movements come into picture only when we shift that point to some reference. Okay. So another definition of center of pressure would be, at center of pressure, there is no movement about the axis. Hence another definition is the point on the body about which movement is zero. The point on the body about which movement is zero. However, in aircraft mechanics or in flight dynamics, we rarely use the center of pressure. The reason is, as the angle of attack increases or decreases, there is an abrupt variation in the location of center of pressure. Alright, but we are looking at how lift, drag and movement are varying with respect to angle of attack. So if center of pressure it keeps on changing location, it becomes difficult for us to analyze the system. Alright. But fortunately, because of the principle of statics, we can shift those forces and moments to our any chosen point. That point can be, as I said, leading edge or trailing edge, or even, as I said, quarter chord point. Alright. Now let us further extend this. So fortunately, using principle of statics, this concentrated force or resultant force R can be shifted to any other point alright, as long as we specify moments. As long as we specify moments about other points. This is very important point. Please make a note of it. You can actually shift this point to our reference point as long as we mention moments about the other reference point. Alright. So if you choose this point to be around the leading edge point, so then you can draw the figure in this way. Alright. So now we will consider this as leading edge. Here we have lift, here we have drag, and this is the movement. So this movement will be movement about leading edge point. Alright, so this figure and this are equivalent. Alright, similarly, we can choose any other reference point, for example, quarter chord point. Okay, if this is a quarter chord point, C by 4, we just have to mention here lift, drag and movement about quarter chord point. Okay, so here we have force at quarter chord point C by 4 plus movement about quarter chord point. Similarly, here we have force at leading edge plus the movement about the leading edge. So this point is worth noting. Always mention the moments about which you are considering the point. Alright, and here I have drawn the convention in this way, that is clockwise direction. If you see here, this is the clockwise direction. So generally the convention is if because of this movement there is a increasing angle of attack or the nose pitches upwards, so then that convention that is known as, we consider that as positive. Alright, so if a moment, let me write it down, a moment which tends to rotate body so as to increase angle of attack is considered positive. Alright, so I am considering here pitching movement. Pitching movement is nothing but up and down movement of the nose. Okay, so here in the figure the movement shown here is actually positive. Okay, this is a positive, it is pitching the nose upward. But generally speaking, for cambered airfoils, we have negative pitching moment. Alright, so movement is actually negative for positive cambered airfoils. Now, what is positive cambered airfoils? We'll discuss in the coming lecture as well. As of now, always remember, for positive cambered airfoils, we have negative pitching moment. So, movement about C by 4 and movement about leading edge will be negative value. Alright, it will be negative values. Okay, now that we are done with this, now let us shift our focus on variation of lift, drag and moment coefficient. Remember, in the last class we have discussed that we have now such a wind tunnel which can have similar conditions where we can simulate good Reynolds number, either good Reynolds number or good Mach number. Alright. Now, if we, after doing such experiments, now we need to analyze our CL, CD and CM coefficients with angle of attack. Alright. And please note, I am denoting here it as a small letter CL, CD and CL. So for wind tunnel experiments, we generally denote it by the small letters CL, CD and CL. I'll explain that as well. As of now, let us focus our attention with CL versus alpha curve. So let me draw a CL versus alpha curve first for a cambered airfoil. Okay. So by default, I will always be considering a cambered airfoil, okay, until unless specified. If I plot the curve between CL versus alpha curve, this curve will be something like this. Alright. So this here we have angle of attack, here we have lift coefficient, and let us consider this as 0.1. Let's consider this as 0.2. Alright. This is lift coefficient, this is angle of attack. And if you see here, this is the point where we are getting maximum CL. Okay, CL max. Alright, this is 0.1 and this is 0.2, and this is the slope, that is dCl by d alpha. And this is the angle of attack at which lift is 0. This is the angle of attack at which lift is 0. So we write here alpha L equals to 0. Alright. Now notice here, for the most practical range of angle of attack, this curve, the CL versus alpha curve, was linear up to till 0.2. Alright. So variation of CL was essentially linear. Variation of CL is essentially linear. With alpha, okay, over most practical range of angle of attack, alpha. The practical range of angle of attack, you can assume it is around 5 to 10 degrees. Alright. So now this slope, this dCl by alpha, this dCl by d alpha is called lift curve slope. Lift curve slope. For thin airfoils, this dCl by d alpha is approximately equals to 2 pi per radian. Okay. Now one thing to note here is, even at alpha equals to 0, we have finite amount of lift. So CL is not equals to 0. Alright. So this is again applicable for a cambered airfoil. So even at angle of attack equals to 0, the CL is not equals to 0. So that means it is producing lift even at 0 degrees angle of attack. Only when we want the CL to be 0, it has to be deflected at negative angle of attack. Alright. For the nose to pitch downwards or the CL to be 0, it has to be deflected at negative angle of attack. Okay. Now see, up to till 0.2 here, up to till 0.2 the curve was actually linear, but after 0.2, what is happening over here? It is drastically losing the lift at 0.2. So at 0.2, flow separation is happening. And this flow separation, we call it as stall. This condition is called as stalling condition. Alright. Now let me draw the figure here. Now this represents 0.1. This figure represents 0.1. Here what happens is, here the flow is actually attached to the body. Okay. Here the flow is attached to the body. But at 0.2, the flow starts separating because of the higher angle of attack. Okay. The flow here actually starts separating, and there is a circulatory motion at the trailing edge. Alright. So this is for 0.2, this is for 0.1. Okay. Now here what is happening is, in the 0.2, here flow separation is happening at the trailing edge. So this condition is known as stall. Okay. Now as the angle of attack is increased, as angle of attack is increased, as the angle of attack is increased, here we have adverse pressure gradient. Now what is adverse pressure gradient? Rising pressure slows flow. Okay, rising pressure slows flow on top surface of airfoil. So adverse pressure gradient on top surface of the airfoil becomes stronger, and at some alpha the flow separates, and at some alpha flow separates. Even intuitively we know, right? We cannot increase the angle of attack up to certain limit, and it cannot keep on giving the lift coefficient as high as possible, right? So there must be a certain limit. So that limit is defined by the stalling limit, and this happens because of the flow separation at the trailing edge of the wing or the airfoil. Okay. Now this we considered for the cambered airfoil. Now if I consider symmetric airfoil, now what happens here to the CL versus alpha curve? Now this is a symmetric airfoil. Okay, so what happens here to the CL versus alpha curve? What do you think? Will there be any changes? Yes, there will be a slight change. Since at zero angles of attack, it will not be able to produce lift. Alright, because here at the same point we have, for example, at this point we have the top force F, and at bottom we have at the top force F. So both are exactly balancing out each other and at the same point, and also there is a no movement. Alright. So because of that there will be no lift at zero angle of attack. Rest the flow, the curve remains similar. Okay, so this is alpha equals to 0 degree. At alpha equals to 0 degree there is no lift. Okay, so this is applicable for the cambered airfoil. Now one more thing. Now here for cambered airfoil, you can see it has a linear curve till point 2. It is a linear relationship or a straight line equation. For the straight line equation, we know it is represented as y equals to mx plus c. Alright, here m is nothing but the slope, c is the intercept. Similarly for this, how can you write for this graph? So in y-intercept we have CL. What is the slope? Slope is the dCl by d alpha. X is alpha, and the intercept is this one. This is the intercept. Alright. So here this we write as lift at zero angle of attack. Okay. So you can write here plus CL at alpha equals to 0. Alright. So CL I can write here CL naught. So CL alpha equals to 0. I can write here CL naught plus CL alpha into alpha. Okay. So CL alpha is dCl by d alpha. Okay. And CL at which alpha equals to 0 written as CL naught. Alright. So always remember this equation. So this is valid only till linear design. So CL equals to CL naught plus CL alpha into alpha. Similarly like straight line equation y equals to mx plus c. So likewise for symmetric airfoil, so what do you think the equation will be? So CL equals to, so will there be CL naught? Obviously no. Alright, so here the straight line equation is y equals to mx. There is no intercept over here. C is 0. So CL equals to CL alpha into alpha. This is applicable for symmetric airfoil. Alright, so never forget these curve. Okay, now next is we have plotted CL versus alpha curve. Now let us see CD versus alpha curve. So remember, these plots we are getting from the wind tunnel results. Alright, so here we have CD, here we have alpha, and the curve is actually a parabolic, something like this. Alright, so in this case, in x-axis, we can also write CD versus alpha, CL curve. So either can be CD versus alpha or CD versus CL, because CL is again a function of alpha. Alright, and another point to note here is, here CD minimum, for example, it is not happening at alpha equals to 0. So this will be at least 2 degrees to maybe 3 degrees or 4 degrees. Alright, so CD minimum does not necessarily happens at 0 angle of attack. Alright, and see, notice here at high angle of attack how CD is increasing parabolically, how the drag is increasing at higher angle of attack. Okay, so remember this point, at higher angle of attack the drag increases parabolically. Okay, now that we are done with the CD versus alpha curve as well, now let us focus on the next curve, that is CM versus alpha. So even before CM versus alpha, let us first focus on CM at C/4. So we are focusing again and again on at quarter chord point. Okay, so let me draw the figure here, that is CM versus alpha curve. So here CM is at quarter chord point. Okay, so here the curve actually it is varying in this manner. Alright, this is the slope. So this slope is dCm C/4 by d alpha. Alright, so here we have alpha. So at this point we have flow separation over the top surface. And at this point we have flow separation over bottom surface. Alright, now this dCm C/4 by d alpha can be positive or negative. Okay, so this can be either positive or negative. But the point here to note here is that this dCm by d alpha is actually constant. This is constant. Okay, for practical range of angle of attack. For practical range of angle of attack. Okay, so now this dCm C/4 is constant for practical range of angle of attack. Now if you consider the CL curve, this is CL alpha, this CL alpha is also constant for practical range of angle of attack. Alright, and this here where we have the stalling at point 2, so this alpha may be around 15 to 20 degrees. Alright, and for fighter aircrafts it can even go beyond 20 degrees as well. Alright, so generally for commercial aircrafts where we have this stalling angle which is around 15 or 20 degrees. So the point here to note is that CL alpha is actually constant up to a certain point. Similarly, dCm C/4 by d alpha is also constant, and this can be either positive or negative. Okay, this can be either positive or negative. What about CL alpha curve? This generally will be positive only. Okay, because we need positive lift at positive angle of attack. Makes sense, right? Okay. So this can be positive or negative, dCm C by 4 by T alpha. Alright. Now let us plot general curve that we were waiting for, Cm versus alpha curve. Alright. Now let me draw curve here. So this is minus, for example, 0.3, minus 0.2, minus 0.1, 0, 0.1, 0.2. Alright. Okay, and this is, we have minus 4 degrees, and this is 0 degrees, 4, 8, 12, and 16 degrees. Okay, and this is the 0 degree line. So let me draw here. Alright, okay. This is one pitching moment, and this is another pitching moment. Alright, draw this again. Okay, now this Cm is about, remember this is a moment, so this will be about some reference point. So this Cm is about trailing edge, and this Cm is about leading edge. Alright, and the point of intersection here is the alpha at which Cl equals to 0. Alright, now notice here, even at 0 degrees angle of attack, we have a negative moment. Okay, so this is for a positive cambered airfoil. So even at 0 degrees angle of attack, we have a negative moment, even though if you consider moment about trailing edge or a moment about leading edge. Okay, so let me repeat this. Even at 0 degrees angles of attack, we have a negative moment, even if you consider moment about trailing edge or moment about leading edge. Now as the angle of attack is increased, then this pitching moment increases about the trailing edge. Alright, this is the curve. Now if you consider leading edge, then as the angle of attack is increased, this moment actually keeps on reducing, as you can see in this plot. Okay, so if you consider leading edge, it is actually reducing. If you consider trailing edge, it is actually increasing. So the point here is that there must be some point about which the Cm does not vary, about some point, right? Cm about some reference point. Cm about some reference point. Okay, now what is this point that we are generally referring it to? So even at this point, if you consider this, if you see this figure carefully, if you see this figure, even at this point we have negative pitching moment. Okay, at this point, even about this reference point, here we have negative pitching moment. So this moment remains at small negative angle of attack. Let me write it here. This moment remains at small negative nose down value that it had at zero lift angle. Okay, so this point is called as is called as aerodynamic center. Okay, remember this point is called as aerodynamic center. So for subsonic speeds, this aerodynamic center is actually very close to the quarter chord point. Okay, so always remember for subsonic speeds, this aerodynamic center, let me denote it by A dot C dot, is very close to the quarter chord point. So even let me write the definition of this aerodynamic center. Here where we have pitching moment. What was pitching moment? Up and down movement of the nose. Here pitching moment is independent of angle of attack variation, of the variation in angle of attack. Okay, so even if you increase or decrease angle of attack, so the pitching, there will be no pitching moment. The Cm will be equals to 0. So that point is known as aerodynamic center. And this aerodynamic center is always a fixed point. So that is what we wanted, right? We wanted some fixed point. The center of pressure was actually changing with angle of attack. Now this aerodynamic center is a point, it is a fixed point where pitching moment is independent of angle of attack. And this aerodynamic center for subsonic speeds is very close to the quarter chord point. Alright, that is what we wanted, right? But however, when I discuss this with students, so it's very difficult to intuitively understand the significance of this aerodynamic center. Whether such a point, whether aerodynamic center exists or not. So this is the question that is being put up by students. Okay. So now let us prove the existence of aerodynamic center. Alright. Now that is the point of discussion. Now consider again an airfoil, the cut section of an airfoil. Alright. Let us assume there is an aerodynamic center. Okay. As of now, let us assume this point you considered as aerodynamic center and this point we consider as quarter chord point. And assume as of now aerodynamic center is behind the quarter chord point. Okay. Okay. And this distance of aerodynamic center is, let me denote this as XAC. Okay. XAC is the distance from the quarter chord point to the aerodynamic center. Now what we are interested is, this is the front portion of the airfoil. We want to prove that indeed aerodynamic center is existing. Okay. So what we'll do, we'll find moments about the aerodynamic center. Okay. Now if we are considering this quarter chord point, this is the lift which is acting at quarter chord point, and as I explained today, if you are considering any point other than the center of pressure, then you have to also mention the moment. Alright. So let me draw a moment here, that is moment above quarter chord point. Alright. Now we will be taking moments about aerodynamic center. Taking moment about aerodynamic center. How can we write the equation? So the moment about aerodynamic center can be written as the force multiplied by distance. What is the force at quarter chord point? The force is lift. And also note, I have mentioned only the lift, not the drag. So since drag is actually parallel to the chord line here. Okay. So we need a perpendicular force. So L is the force and the distance is L into XAC plus the moment about quarter chord point. Alright. So we have just taken the moments about aerodynamic center. The moment aerodynamic center is lift into the distance xac plus moment about quarter chord point. What we'll do is we'll divide this equation, divide by qsc, okay, on both sides. So what do we get? Moment about aerodynamic center, qsc equals to L divided by qsc xac plus moment about c by 4 qsc. Remember in the last class I have also mentioned the equation for lift, drag and moment coefficients. So Cm cos m by half rho v square s c. This is the reference length. Please do not forget this is a moment. Alright. Now this can be represented as, using this equation, this can be represented as CMAC. CMAC, and what is L by QSC? PL was L by QS. Okay, not C, this is a force. So now you have CL XAC by C. Similarly, this one CM C by 4. I hope there is no confusion here up to this point. Okay. Now remember why we are doing this exercise. We wanted to know the variation of the moment coefficients with respect to angle of attack, and is there any, do we have this point existing or not? Okay. So to know the variation of angle of attack, we have to differentiate this equation with respect to angle of attack. Differentiating with respect to angle of attack alpha. So now I can mention this as DCM AC upon D alpha. Okay. Here we have DCL by D alpha. Okay. DCL by D alpha into XAC by C plus DCM C by 4 by D alpha. Now look at this equation carefully. Which term do you think is actually going to 0? Which term in this equation do you think is actually going to 0? Yes. We have just now defined the definition of the aerodynamic center. The aerodynamic center is a point about which the pitching moment is independent of the angle of attack variation. Okay. So that in mathematical point of view, you can write here as DCM AC by D alpha equals to 0. Alright. Okay. Now let us substitute this equals to 0 equals to DCL by D alpha XAC by C plus DCM C by 4 by D alpha. Okay. Now let us proceed further. Here I can mention it as XAC by C equals to minus DCM C by 4 by D alpha divided by DCL by D alpha. Now remember this equation, DCM C by 4 by D alpha. This was actually a constant value. Okay, this is having some constant value. So, what about DCL by D alpha? That is the lift curve slope, CL alpha. This was also a positive constant value. So that means what? Here we have some number divided by some number and negative sign. So that means aerodynamic center point is actually existing. Okay. And if I want to non-dimensionalize this, x bar AC equals to, I can write in this way, minus DCM C by 4 by D alpha by DCL by D alpha. Alright. So this we generally write it as non-dimensional form. Not only this x AC bar, whenever I mention bar over some term, so that means that is non-dimensional line. Okay. So now we have this constant number, constant upon constant, hence this means, hence we get finite number for x AC bar, indicating aerodynamic center does exist as a fixed point on the airfoil. Alright, now let us quickly do an example based on this aerodynamic center. Now let us consider for NACA 2412 airfoil. Okay, so after doing the experiments in wind tunnel, the variation of CL, CD, CM with alpha is now known, and here we have the results at alpha equals to minus 8 degrees. Here CL equals to minus 0.6, and at alpha equals to 8 degrees, here we have CL equals to 1.08. Again, at alpha equals to minus 8 degrees, CM C by 4 equals to minus 0.045. And at alpha equals to 10 degrees, CM C by 4 equals to minus 0.035. Now look at these values carefully. Okay. So whenever I give these values to students, I always instruct them to plot these rough plots with these values, so that it gives you an idea how the curves are varying with respect to angle of attack. Now let us first plot CL versus alpha curve. Okay. CL versus alpha curve. So at alpha equals to 8 degrees. So at alpha equals to 8 degrees, we have at alpha equals to 8 degrees, CL equals to 1.08. So consider this as 1.08. Alright. And at alpha equals to minus 8 degrees, at alpha equals to minus 8 degrees, for example, this is minus 8 degrees. Okay. At alpha equals to minus 8 degrees, CL equals to minus 0.6. Now consider this as minus 0.6 point. Now join these two lines. Okay. So here we have CL equals to 1.08, and here we have CL equals to minus 0.6. Okay, so this is CL versus alpha curve. Similarly, now let us plot for CM versus alpha curve, that is CM C by 4 with angle of attack alpha. Okay, so now we have given at alpha equals to minus 8 degrees, CM C by 4 is minus 0.045, and alpha equals to 10 degrees, CM C by 4 is minus 0.035. So let us consider alpha equals to 10 degrees, this is 10 degrees, this is the value of CM, which is around minus 0.035. Alright, next at alpha equals to minus 8 degrees, so for example this is minus 8 degrees, here we have minus 0.045, it is even lower than this, minus 0.045. Now join these two lines. Okay, so remember I have roughly plotted previously the curve for this CM C by 4 with alpha. So this was actually having a linear curve at for practical range of angle of attack where it was constant. So here even in this figure you can note there, even though it is negative, but the slope is actually positive, okay, but the moment is actually negative, but it is increasing as the angle of attack is increased. Okay. Now that we have these plots, now let us quickly solve the question that we have, and the question is to find the aerodynamic center. Alright, now we quickly have to find the aerodynamic center for this airfoil NACA 2412. Alright, okay. Now before finding the aerodynamic center, we need to find the slope of these two plots. So this is PCL by D alpha or CL alpha. Similarly, this is DCM C by 4 by D alpha. Okay, so these are the slopes. So how do we find slopes? So DCL by D alpha here we can write CL2 minus CL1, that is 1.08 degrees. This is 1.08 degrees minus of minus 0.6 minus of minus 0.6, then divided by x2 minus x1, that is 8 degrees minus or minus 8 degrees. Alright, 8 degree minus of minus 8 degrees. So what do we get here? 0.105. Now what will be the unit of this? That is CL alpha. So when I ask this question to students, they mostly will say that it is unitless since it is a coefficient. Now let me ask you, is the unit of CL alpha unitless? Do you think the CL alpha unit is unitless? The answer is obviously no. This is CL alpha, dou CL by dou alpha. Okay, so the unit should be per degree or per radian. Alright, we have alpha in the denominator term. Okay, makes sense? Alright, so since we have used degree over here, so this unit will be DCL alpha 0.105 per degree. Alright. Now similarly, find DCM C by 4 by D alpha. Alright. Here we can write minus 0.035 minus of minus 0.045 divided by 10 degrees minus of minus 8 degrees. Alright. So what do we get here? Let me just write down here, minus 0.035 minus of minus 0.045, alright, 10 degrees minus of minus 8 degrees. So this you get 5.56 into 10 to the power minus 4. Yes, it will be very small number, and the unit of this will be, yes, it will not be unitless, it will have its unit because we have alpha in the denominator. The unit is per degree. Alright. Now we have XAC upon C. The equation was minus DCM C by 4 by D alpha divided by CL alpha. You just have to divide these two numbers. So what do you get here? Minus 0.0053. Alright. So now if the chord length is given to you, then you just multiply this number by the chord length C, and then you will get the location of aerodynamic center. Alright. So this is the location of aerodynamic center with respect to chord. Alright. Now what does this negative sign mean? What does this negative sign means? Here, while deriving this expression, we took the assumption that aerodynamic center is behind the quarter chord point. So here negative sign means for this airfoil, the aerodynamic center is ahead of the quarter chord point. Okay. So always remember the sign. So minus 0.0053 indicates that AC is ahead of C by 4, that is 0.53% of chord length. Alright, so the one point you must have noticed that this point is very close to the quarter chord point. Okay, as I mentioned before as well, the aerodynamic center will be very close to the quarter chord point. Alright, so in today's class we have discussed about the significance of the aerodynamic center, which we came to know it is actually closer to the quarter chord point. And in the next lecture, we will be discussing the relation between the aerodynamic center and the center of pressure. Thank you.